don't pay for the electricity that they consume. The government heavily subsidizes the rate that people pay. But because of very poor tax collection, the government can't actually afford to pay the subsidies to the power producers, who in turn can't pay the fuel suppliers and down the line. So eventually, power generation facilities have to shut down. The magnitude of this circular debt is estimated at between $3 and $5 billion, which is approximately 2% of GDP in Pakistan. So unless and until households and business consumers in Pakistan either pay for power or pay their tax bills, it will be very difficult to solve this particular governance challenge. And until now, the government, out of fear of social unrest, has shied away from either raising the rates or shutting off power to consumers that are delinquent in their payments. So how does nuclear power fit in this rather grim picture? As I noted, it currently makes up about 4% of electricity generation. In the next couple of years, with 2 nuclear power reactors supplied by China coming online, this figure may rise to about 7 or 8%. And over the next decade, if construction is completed on 2 very large reactors being built by China on the outskirts of Karachi, the percentage might rise to perhaps 15 to 20% of total electricity generation. This could undoubtedly make a dent in the supply deficit. But these figures tell only a very small part of the story. In order to build the bridge between nuclear energy and peaceful coexistence, we need to consider some additional context. So I'd like to spend a few moments exploring the politics of nuclear technology, which bear heavily on Pakistan's future course. And we can't talk about politics without also understanding something of the technology involved, so please bear with me for a few moments. The fundamental source of both nuclear energy and nuclear weapons is uranium. Like other natural resources, it is mined, processed, and converted into fuel, in this case for nuclear reactors. But unlike petroleum energy, which is fully consumed once its thermal value has been utilized, the use of uranium for energy has 2 inherent points of weakness that have major security externalities in terms of weapons proliferation. The first comes in the process of converting uranium into fuel. Now, uranium from the ground is about 99% comprised of the isotope U-238. Now, U-238 is not a highly fissile material. I don't expect that any of you are nuclear engineers, and for that matter, I'm not either. So let me briefly explain that the fissioning of uranium releases energy in the form of heat that then turns the turbines that produces electricity in a nuclear reactor. That's kind of a gross simplification, but basically captures it. So to increase the efficiency of chain reactions in large nuclear power reactors, the uranium must be enriched, which involves using an industrial process to separate and increase the percentage of the isotope U-235 that makes up the 1% of natural uranium that isn't U-238. Now, in most reactors, like the Calvert Cliffs ones that aren't far from here, the fuel has been enriched to about 3.5% U-235. But U-235 is what is called a direct use material, meaning at high concentrations, it can be used in nuclear weapons. Thus, the process of enriching uranium for nuclear reactors is the same as enriching fuel for nuclear weapons. The second point of proliferation weakness arrives after nuclear fuel is burned in a nuclear reactor. During the fissioning process, some of the uranium transmutes to plutonium, which is another direct use material for nuclear weapons. Now, the plutonium and uranium are contained within the spent fuel, which is highly radioactive after it's been used in the reactor. But after the fuel has cooled, these elements can be chemically separated through an industrial method called reprocessing. Sending spent fuel through a reprocessing facility has a number of benefits in terms of reducing the waste volume associated with nuclear power, and it can potentially be used to recycle some of that fuel, which is why states such as Japan and France, and even at one time the United States, pursued it. But it can also result in the accumulation of large quantities of plutonium, which poses a major nuclear security risk and also a non-proliferation risk. For context, it takes about 10 pounds of plutonium or maybe 20 pounds of highly enriched uranium to make a nuclear weapon. And in the context of large industrial processes, these are relatively small quantities. Both technologies, enrichment and reprocessing, have peaceful uses, but one or both must be used if a state is going to pursue nuclear weapons. This raises a critical question about nuclear power: how to ensure that the use of these technologies remains peaceful? Or stated another way, if technology for energy and technology for weapons is fundamentally the same, how do you create an international governance structure that establishes incentives that encourage states or deters states from crossing the threshold to nuclear weapons? The answer adopted by the international community over the decades since nuclear weapons were developed and used by the United States in 1945 highlights the inherent tension between energy and weapons. The 1968 Nuclear Nonproliferation Treaty, which is the cornerstone of the global nuclear order, permits just 5 states to possess nuclear weapons: the United States, the Soviet Union and Russia,